My name is Diego and my partner's name is Angel, and this video is for our tolerancing and scenario project for manufacturing processes section 1 with Professor John Bergman. And in this video we're going to be analyzing a door hinge. So the parts that make up a door hinge are the left leaf, the central pin, and the right leaf, and when they are all assembled, it provides for a smooth rotational movement for opening and closing doors, and it also provides stability and support for the door's weight. So as we progress through the slides, we're going to be analyzing each and every single component here for their G, D, and T, and we are also going to be doing G, D, and T for the screw holes and the relationship between the pin and the knuckles right here.
Process of door hinge leaves. The process starts with metal sheets, in our case 12 gauge 3/16 stainless steel sheets. They are fed into a punch press where they are cut into desired shape and uniform flatness. They are then taken to a CNC drilling machine where the screw holes with countersinks are drilled into the desired location. A drilling machine is then used to roll the individual sections of the hinge leaf into cylindrical shapes to form knuckles. The parts are then heat treated to improve its mechanical properties. Finally, it undergoes a chemical treatment to protect against corrosion and oxidation called passivation.
The manufacturing process of the pin starts off by hot rolling the raw material into a round bar with a rough surface. After that, the heat treatment and annealing process starts off, and we do this so we can improve the ductility and toughness of it. Then the tubing is cold drawn to get that smooth surface finish, desired shape and size. And then finally, using cold forming, which is a high dimensional accuracy rapid process that stamps out the final shape using dies so the material isn't wasted, we're able to get that final pin shape.
Flatness, parallelism, and perpendicularity tolerances. Flatness ensures hinge plates seat securely against the door frame, preventing gaps or uneven load distribution. Parallelism ensures proper alignment of hinge knuckles, allowing smooth rotational motion without binding or excessive wear. Perpendicularity guarantees alignment of the hinge's rotational axis with the door, ensuring smooth operation and minimal resistance. For these three alignment parameters, we chose a tolerance of 0.004 inches. We chose this tolerance because of manufacturability, inspectability, cost performance balance, and reliability. This tolerance is easily achievable and repeatable with current modern manufacturing processes. It is also verifiable with standard tools like height gauges and coordinate measuring machines. This tolerance ensures the precision for long-term durability, smooth operation, and resistance to wear or misalignment without adding unnecessary manufacturing costs. In the door hinge left leaf drawing, we can see that datum B has a flat tolerance of 0.004 inches, so that when the hinge is placed against the door or frame, it sits flat. Datum C has a perpendicular tolerance of 0.004 inches with reference to datums A and D, but it also has a flatness tolerance of 0.004 inches. Datum D also has a perpendicular tolerance of 0.004 inches with reference to datums A and C. These three tolerances control the shape of the hinge to be rectangular. The door hinge pin drawing shows that datum B, the underside of the pinhead, has a flatness tolerance of 0.004 inches. This is so that when the pin is inserted into the knuckles, the pin sits flat on top of the first knuckle. The drawing for the right leaf is similar to the left leaf. Screw hole tolerance. To fasten the hinge to the door or frame, we are using number 10 by 1 inch flathead Phillips stainless steel screws, which are coarse threaded and zinc plated, specifically suited for wood applications. The focus here is on achieving a close fit between the screws and the through holes. The chart gives us the values for the nominal diameter of the through hole and the countersink. To ensure we have a tight tolerance, we set the diameter tolerance to plus or minus 0.005 inches and the angle tolerance to plus or minus 1 degree. These tolerances are critical because they ensure a proper fit between the screw and the hole. They avoid excessive clearance which could otherwise lead to misalignment or looseness, and prevent interference that might hinder assembly. Additionally, we maintain a positional tolerance of 0.008 inches, which helps in the precise alignment, ensuring the hole is straight and not askew. Since the depth of the hole is only the thickness of the hinge, the positional tolerance does not have to be as tight as some of the other positional tolerances. We apply these measurements and tolerances to the three screw holes on both the left leaf drawing and the right leaf drawing.
Lastly, we have the pin and knuckle tolerancing. So the pin interfaces with both the left and the right leaf hinges, and we wanted to go with the minimum clearance so the slack and the droopiness of the door is completely avoided. We went with the medium fit, so we referred to the chart in the bottom left corner where we could match the inner knuckle diameter to the hole diameter on the chart and the pin diameter to the shaft diameter on the chart. And looking at our drawings, we see that the diameter tolerance is unilaterally positive 0.0008 inches for the inner diameter, and for the shaft, it's the diameter tolerance is negative unilaterally of 0.0006 inches. And so when you put these two together, we get that minimum clearance of 0.0002 inches, which is what we essentially want so we could avoid all droopiness and slack on the door. Here's our references, and thank you.